Hi, I'm Ben-Yaakov. This presentation is entitled Transparent Isolated DC-DC Converters. Let me just note that the commercial devices that are shown in this presentation are only an example, and there's no endorsement or recommendation implied here. And also I'm not affiliated with any of the companies mentioned. Now, the classical switch mode DC-DC converters are based on either a switched inductor. For example, we have here a buck and we are switching this inductor so as to pump in energy to the output. And then we have another class, which is a switched capacitor converters, in which we charge a capacitor, the so-called flying capacitor, and then transfer the energy to the output. In this case, we see a inverter. In some cases, we are looking for an isolated DC to DC converter, and we really don't need to have regulation if we are filling the DC-DC converter with a fairly fixed voltage. So these cases will be like when we like to have an isolated local power supply, for example, a high side drive supply for a half bridge. We like to separate digital and power grounds, and also in some cases we would like to have low input to output capacitance, and this will be an example for a high side drive or a very fast half bridge configuration. And by designing our own isolation transformer, we can design it for low capacity. Now, the basic idea is shown here. It's very simple. We have a transformer, a rectifier, a bulk capacitor, and then we have the output. And the operation is based on the fact that we are feeding in a square wave, and then of course when we have a positive voltage, then two diodes are conducting, let's say D1 and D4. So what we have is we are imposing the voltage at the output of the transformer. We're imposing it on the output through these two diodes, and then on the negative voltage phase, the other two diodes are conducting, and again we are imposing the input voltage after transformation to the output. So it's just like connecting the input to the output through a transformer. That's what it is. Or we can say that basically we have just overall a voltage source, two diodes, and then we have the load, and we are imposing the voltage here on the load. In a practical system, we're going to have some resistance. This will be the switching, the wires, etc. So we would expect some drop due to the voltage drop on the resistor. So there's a drop here, and this will depend on the total resistances in the circuit. If you run a simulation on the ideal circuit, here is what we get. This is the input pulses, this is the input current, this is the current at the output of the transformer, and here is the output voltage, practically almost no ripple. And this is because we are just imposing the voltage of the input through the transformer or the output. So this will be for an ideal system. Unfortunately, life is not that simple, and we do have leakage inductances. Now, due to the leakage inductances, we have it here, we can separate them to the primary and secondary. Then we have to build up the current on each half cycle. We have to build up the current, and therefore we are going to have an effect of this leakage on the performance. Just to see what happens, I am illustrating it by a simple simulation. It's a PSPI simulation. We have a source. This is a square wave, plus minus 15 volt. Here is the transformer, and I've reduced the coupling to 0.85, so this system now has leakages, and I've inserted a 100 milliohm resistance. There is a blocking capacitor it is needed even in simulation, because if the waveform is not absolutely symmetrical, you have a residual DC voltage, and this, without a capacitor, will start building up a current through the inductor. So in the practical system and even in simulation, we better put a DC blocking capacitor. And then we have the output side. This is a bridge, and the output filter capacitor, and the load, which is 100 ohm here. So here is what we get. This is the input square wave, and this is the input current. This is the transformer output voltage, and this is the output current coming out of the transformer. So what we see here, let's concentrate on this particular curve here. What we see here is that the current is building up during the time that the pulses stay positive. When there is a transition, we see a high voltage on the leakage, so there is a fast drop. And then on the negative phase, we do have again the buildup of the current across the leakage inductance. So basically, we're not having a transparent operation, but it is going through a inductor that has to be charged one way and then charged the other way in order to pass the current from input to output. So in general, we're going to have at the output a triangular waveform, the current building up. Now the average here is of course the output current, and the peak value in this case will be twice this average, being a triangle. The IDT will be related to the voltage across the inductance. Here it's shown the total leakages, and of course the value of the inductor. So we can say that the voltage across the inductor, I'm assuming now a constant voltage during this period of time. Strictly speaking, this is not entirely correct because we have a voltage drop here which is changing, but let's assume that this is about a constant voltage. And then the IDT is the total change is twice I average, and the time here is 1 over twice the frequency, it's half the period. So this comes to be L times 4F I average. So therefore we can say that the voltage divided across the inductor divided by the average current is this expression here, which is sort of like a resistance. Okay, so we have an added resistance here for expressed as a function of the average current here, and the value of it is 4F, the switching frequency, and L. And this makes sense because if we have a large leakage inductance, then obviously the voltage drop across it will be high. And if the frequency is high, we just don't have sufficient time per half period to build up the current, so therefore the delta V has to be larger. Okay, so this is a voltage drop we have here, and obviously the drop will be much larger than we assumed before without taking into account the leakage inductance. So here is a simulation I have run for a leakage inductance of 20 microhenry, frequency of 200 kilohertz, and calculating the equivalent resistance, we find that it is 16 ohm. And here is the run. This is running it for different currents, okay? And we see as the current builds up, there is a voltage drop. And here we see the output voltage as a function of the output current. And looking at this slope here, I see that for a 100 milliamp, we have a drop of 1.3, so it comes out to be 13 ohm. Well, it's not exactly what we calculated, and there are many reasons for it. We'll talk about it later on, but we see that in the ballpark we are apparently correct here and that we understand what's going on. The larger the frequency, the larger the inductance, the larger will be the voltage drop due to this apparent resistance. Here is another run. In this case, the current is constant, the frequency is 200 kilohertz, and we are changing here the inductances. This is for different inductances. Here is the inductance. That's between, say, 5 microhenry to about 50 or 60. And we see here again very nicely as the inductance, the leakage inductance is going up, there is a substantial voltage drop. So the culprit here is really the leakage inductance, which is causing the voltage drop. So obviously, if one cannot tolerate the droop, the voltage drop due to this internal resistance, then there's always the option of putting an LDO. There is some loss penalty involved, but not that much, because you can keep the voltage drop on the LDO pretty low, and therefore this will be one way to get a fixed output voltage even when you need it. So what about the losses here? What about the efficiency? Well, obviously it will be a function of the conduction losses. This is the total resistances, like if you have a MOSFET, the RDS-on, wires, etc. Then we have core losses, which are proportional to delta B, that is the change in the magnetic flux density. And then we have diode losses, of course, and this is why you'd like to use a Schottky diode, which have a much lower voltage drop, if you can, if the voltage is low enough, not above 100 volt. So these are the losses, and depending on the design, you can get decent efficiency. Now a transformer will have also a magnetization inductance. So the question is, what's the effect of this magnetization inductance? Now obviously, if you have here a inductance, and if the value of the inductance is low, you'll have here a circulating current through this inductor. In fact, if this is a square wave, you have a triangular waveform of a current flowing through this inductor. So first of all, it's going to increase losses because there's higher current through the drive. You have MOSFETs here, so the RMS times the RDS-on will increase. But this circulating current, or this loading, has some beneficial effect because it is sort of diluting down the effect of the load. Because if you are carrying current here already in the leakage, then the additional current due to the load, proportional wise, will have a smaller effect. So on one hand, efficiency goes down. On the other hand, regulation or stability is improving. So it's a conflict here between these two requirements. Now what about cross-regulation? Now obviously this system will also suffer from the problem of cross-regulation. That is, if you have more than one output, and you can have a number of outputs, no problem in that, but when you load one of the output, it will affect the other output, because once you load it, there is a larger voltage drop on this leakage inductance, and therefore the voltage here will be lower, and you will see it here. And again, the culprit here is leakage inductance. The smaller it is, the better will be the stability. So how can you minimize leakage inductance? Leakage inductance due to the fact that some of the flux of the wires is not common. It's not passing through the core, but rather being around each of the wires. And this will be correct in this case, and also if you wind wires, the winding is one on the top of the other. One way to reduce the leakage would be to use bifilar winding, that is to take the two wires, say primary and secondary, and then to wind it together. By this, you minimize the stray fluxes, and the flux is sort of common to the two wires. Now this, however, increases the interwinding capacitance, and in some application this is something that you have to worry about, and you'd like to keep the interwinding capacitor small. So again, it's a compromise here. Using bifiller will improve and reduce the leakage, but then it will increase the capacity. So how can we build a system like this? There are many ways to do it. One possibility is to use a half bridge with a capacitor, of course. Then this will block the DC, which is now dominant here. And in this case, we need two drivers. If we use N-channel transistors, a high side and a low side drive. And then, of course, we have the inputs here, which are in 180 degrees, one with respect to the other. So this would be one way to do it. Another way, which is really very nice, is to use a push-pull configuration. Two transistors. This is a push-pull transformer, and actually we can use a half-wave rectification in the output. We can also use a full wave, as I've shown before, but the half-wave is more economical, although there are more windings. Again, there's a problem of capacitance here. And in this case, the nice thing is that the drivers are referred to ground, simpler way to drive the transistor. As it turns out, this solution is available as an IC device made by Texas Instruments. It's a SN6501, and as we can see here, it contains everything that is needed as far as the drive goes. We have the oscillator, we have the gate drive, and then we have the two transistors. And this is designed for 5 volt, up to 5 volt or 6 volt, and 3.3 volt supplies. And here are the maximum currents that you can get for each of them. And of course, they are showing here the application. As we have noticed, there could be many applications to a unit like this. Now here is an example of a very simple system. We have this unit, we have the transformer, 2 Schottky diodes, and a capacitor. That's it. That's the whole thing. Here it's nice to have a bypass capacitor close to the chip here. And here they're showing the output voltage, and here's the droop we talked about, and the efficiency, which is pretty good. In this case, it's about 85 in mid-range. This is for a input of 3.3 and output of 5 volt. So this is a fairly nice performance, but again, it is sort of limited in the voltage range and in the power that you can transfer through it. Now, Worth company has a line of transformer which are actually designed for this application, and you can get it for different transfer ratios. These last 2 digits actually designate the transfer ratio, so you can get it as an off-the-shelf item, very convenient. And here is an example of one of these transformers. It's about 10 millimeters, so 1 centimeter square. It's a small transformer. Here's the input or output, or vice versa. You can use it either way. And here's the information about the resistances. It's about half an ohm primary and secondary, which is okay for the current that we are talking about. Here is the primary inductance, 475 microhenry, and although it is measured at 10 kilohertz, while the unit itself, IC here, is actually running at 350 or 500 kilohertz, so it's a much higher frequency. And the information that they give here is for 10 kilohertz, but as far as the inductance, there will not be a big difference. But there's no information about leakage or core losses, so you really have to get one, try it, and see if it fits your application, and also there is no information about the input to output capacitance, which in some application could be very crucial. So these are available, variety of transfer ratios, but again, you'll have to really test to see if it's doing what you need. Now, Texas Instruments gives in the datasheet some information about performances, and there are two test circuits that they are showing. This is the basic one, and then there is one with an LDO. Okay, so there are two test points. This is TP1 without LDO and TP2 with LDO, and here are some graphs. There are many more in the datasheet. So what we see here is, first of all, the output voltage as a function of the load current. Now TP1, which is the basic circuit here, has this group here. TP2, which is after regulation, after the LDO, of course, is very constant. There's no trick about that. Now we see here also the efficiency. TP1 is fairly high, it's about 85. TP2 is somewhat lower, and this is because of the extra voltage drop on the LDO, and you lose the efficiency, but of course you gain stability. And here there's another plot. Again, TP2 is constant. This is for 3.3, and the droop here is lower. You see here, much lower than here. So what's the reason for that? Well, first of all, we are in a different transfer ratio. Here is 5 volt in and 3.3 out, and here it is 3.3 in and 5 volt out. And these are two transformers. So transferring the leakage to the output in these two cases could be different. Also, the magnetization LM, magnetization inductance in each of these cases is also different because of the transfer ratio and direction. And as we can see here, in fact, the efficiency is much lower. So this is consistent with what we have seen before. So this brings me to the end of this presentation. I hope you found it interesting, and perhaps it will be useful to you in the future. Thank you very much.